Hello everyone. So I'm gonna present one of the applications that UCL is gonna use during the VECMA project, which has been developed during the Compat project. So we usually call it an HMM. So in that case, H doesn't mean hierarchical, but as it could mean in other multiscale modeling techniques. So it's heterogeneous, which I will explain why later. And we use it to model polymer nanocomposites and try to upscale their properties from the nanoscale, the atomistic composition, to the macroscopic scale, where it could be applied to industry. I'm going to dive right in. So at the nanoscale, we use composites that are usually made of, so in the case of this picture, clay sheets and polyethylene, but as I will show you later, I'll rather use epoxy resins, which are slightly different. And what we do with them is we try to predict the mechanical behavior of structures that are typically used in aeronautics. So, for example, an engine for one of these recent planes that Boeing or Airbus can develop. So the two methods that we use in the HMM are molecular dynamics that basically solve Newton's equation of motion. The degrees of freedom are basically the position and the velocities of all the atoms in a box of the material. And on that, we use force field to understand, or actually to control the motion of atoms with respect to each other. Some of these force fields are simpler to integrate than others. For example, OPLS is an elastic force field, so the interaction between the atom will not change during the system, during the simulation. But if you want to capture some nonlinear mechanisms, such as fracture or like void growth of the epoxy that you want to study, you have to use more complicated force fields, such as the reactive force field. But this can increase drastically the computational time up to 50 times on average. On the macroscopic scale, what we use is continuum mechanics that we solve using finite element method. That basically means solving the linear balance of momentum. And to do that, we use, so I didn't mention, so for the molecular dynamics, we use a standard library called LAMMPS, which is highly parallel. And on the macroscopic scale, we use another finite element library, which has some more or less good properties of parallel properties, and called DIL2. And so typically in finite element model, what you have is in each of these cells of your mesh, you have a relation that you need to get between the stress of in the material and the strain, which needs if you're only doing a single scale model to parameterize you need these parameters to fit the model. And so the whole purpose of a multiscale model is to remove the issue related to the estimation of those parameters. So to do that, you have multiple options. So what is actually called hierarchical coupling is you run instead of doing experiments on your material to get those KIs, those parameters in the model, you actually run an anoscopic or a smaller scale model, which you will test over a whole range of conditions, and you'll get those parameters that you'll feed to your macroscopic model. And then you'll perform the simulation in which you need to understand if your structure is going to be sustainable or not using those parameters. So that's hierarchical coupling, which is a one-way coupling. So you only run the microscopic model, the lower scale model once, and then the higher scale model after. But you don't have a feedback between the two. HMM, which I denote as weak concurrent coupling, is you have the two models completely separate, and you iterate going from one to the others. And so instead of having to formulate that kind of law, which can be very complicated, because it holds many parameters. It is not true in every temperature or strain rate or any type of conditions. You avoid that by running a lower scale simulation anytime you need to actually get the stress in one point of the model, given a certain strain. And so you run many of these micro simulations. And then the last one is strong concurrent coupling, which you can find in the literature under the name of quasi-continuum, for example, or bridge scaling method. Scale bridging method, sorry, SBM. So instead of having the two separate models in your workflow, you actually have them in a single solver. So you solve them concurrently, like literally at the same time, simultaneously in the on your computer. And so what we're going for is in our application is for the HMM one, which has two simple benefits compared to the others. Your model being completely independent, you rather have to work on the workflow and the scalability of the independent models rather than how you're gonna solve two different methods in the same time as you would with the strong concurrent coupling. So the workflow looks like that in the end. So basically, what you do is so in light blue, that's the boxes that correspond to the finite element solver. In red, red being these ones, you have the work performed by LAMPS, by the molecular dynamics model, and in purple there you have the phase which is taken care by the coupling library between the two models, or what we actually develop here, which performs the transfer of data between the two models. So what happens is that using your finite element solver, you'll predict the displacements of the nodes of your structure. You can compute from that the strain in all of your correction points in your cells. You feed that to your molecular dynamics model, which in turn gives you back the stress. Then you have to homogenize it, which I will discuss a little bit after that. And then these stresses are returned to the macroscopic model, which checks if the balance of linear momentum is still verified, and then you iterate like this, advancing in time. A small specificity of HMM workflows is that since you actually will not need to compute the stress in every quadrature point of your model, you have a variable number of ND jobs to run, or actually maybe not the variable number of ND jobs, but a constant number of ND jobs with a variable length in time, which makes the load balancing quite complicated. Okay, forget about the part on the right. So basically, how we separate the scales in the models to actually gain some time instead of just simulating the whole structure, the whole macroscopic structure with an atomic resolution. The gain from doing a multiscale to a single scale approach is basically explained by these two figures. So in time, what you do is instead of running the ND simulation for the whole time step of the macro solver, you only run it until the atomistic system relaxes. So let's say you have a transient mechanism there in green at the atomistic level. So as soon as this gets stationary, you can basically stop your atomistic simulation and feed back the stress that you measure. And so you don't have to compute that whole bits of time, and you can advance like this in time. So this is of the order of, let's say, at most in a few nanoseconds. And the increment in time in blue there might be a few, so I said nanoseconds there, microseconds at the top. So you have a massive gain in time. In space, it is kind of the same, so it's the same idea. You have your whole volume of your cell of the finite element model. Instead of simulating this at the nanoscopic with the nanoscopic resolution, let's say, so at the nanoscopic scale, you have heterogeneities, which are, let's say, these green dots in the figure. So you only have to simulate a few times that size, plus applying periodic binary condition to your system, and you have basically an equivalent system. So the gain, once again, is the ratio between that length and that length. This being a few nanometers, and this being a few micrometers. So you can compute you can have a massive gain by decoupling the scale. So this is a quick recap of the data the data inputs and outputs of the two models. So the continuum model at the continuum model, what is constant is the density of the mesh and the strain rate, which is specific to the macroscopic model. And then at every time step, you feed your atomistic model with a strain and a specific strain for the cell. The number of atoms, the temperature, and the strain rate are fixed in our simulation, and then you feed back the stress. So one of the major problem of the scale bridging procedure is actually homogenizing, transferring the stresses from the atomistic simulation to the macroscopic model. So if you let your system, if you take a replica of your epoxy resin, for example, and you let it, so you set it at constant volume, number of atoms, and temperature for a few here femtoseconds, no, picoseconds, 20 picoseconds. What you see is that you have an enormous fluctuation of the stress, which is simply due to thermal fluctuations, and you need to actually be able to average the stress to get to know how long you have to average the stress and over which amount of replica you have to average this to actually get the actual stress in your system. So to do that, we actually to determine how long we check the autocorrelation function of the stress fluctuation on each replica, and what we have is something that is of the order of so it is the order of it was 100 time steps, which makes it 200 femtoseconds, just femtoseconds. And so that's the that's how we determine the autocorrelation length of the stress fluctuation, and we check how long we needed, how many autocorrelation length we needed to compute or to have a reduced confidence interval, 95% confidence interval on the stress. And so that's so we arbitrarily choose like 0.5, 0.4. So that's 40 femtoseconds. That's 40 picoseconds to get the stress. We homogenize and feed back to the. So we choose that by checking so if we increase more this time of sampling more than that, we would have a very low gain compared to what we had before. So it wouldn't be actually worth going a lot further to reduce the confidence interval. That's quite arbitrary. For the choice of number of replica is pretty much the same. So you get the same type of curves, or as you increase the number of replicas, you narrow your confidence interval, and when you don't have much gain, you just stop. So in that case, 8 replicas were chosen. So I'm gonna now switch to a quick demonstration of the use of multiscale methods in the case of materials. So typically, when you want to predict the fracture toughness of a material, what you do is, so people that do single scale model or actually hierarchical scale, multiscale model, they say that they can fit the macroscopic parameters on a single MD simulation without doing any feedback between the scales. And so, for example, when they want to assess the fracture toughness of the material, what they do is a pure, what we call a pure tension, uniaxial tension test on a batch of epoxy resin. So in that case, what they get is, so they do the simulation that you see on the right on the epoxy, and they get that kind of curves, which gives the stress as a function of the strain, and the fracture toughness is simply the area under the curve. So and from that you move to a multi-scale approach where you actually use at the macro scale the setup that is used in engineering tests. So this is called the compact tension test, and so you have a specimen with these two holes, which is pre-notched up to there, and then they pull on it, like they just pull vertically on it, and the crack propagates there. And what they measure is the energy to break these two pieces apart, and that's how they derive the parameters that they use in their finite model to do some structural engineering. So so what I want to show you is the comparison of what actually happens in those cells at the crack tip, what kind of tension, what kind of mechanical state they face in there, compared to what is hypothesized in these single scale or hierarchical multiscale methods using pure tension. And so that's actually how the green cell here is deformed when you pull it as part of a compact tension. So it's not anymore just a pure tension, so it's actually a biaxial tension. You pull in two ways, and then you have shear that comes on top of that. And the resulting behavior, so that's the complete strain tensor that you get. So you have these two main components of like pure of tension in the XX and YY directions, and then you have a little bit of shear. So actually, so yeah, you have XY shear coming out of this. And so if you compare the two results, so at the final states of the two materials, so in uniaxial tension, you have this type of fracture. You have a mass, like a localization of the void growth there, and you have more or less a normal crack to the loading direction. While in compact tension, what you have is a more diffuse void growth all over the sample, and actually you don't have the same final geometry at all at the end. And so this impact significantly the fracture toughness you determine from that. And so if I give you back the curves that I showed you at the beginning, so the stress strain curve of the material, so the blue one is for uniaxial tension, and the green one is for the compact tension in the most loaded direction. And what you see is that the fracture toughness that you would derive from a pure uniaxial tension is actually massively overestimated compared to the area under the green curve that you would get from a compact tension test. That's it. So that was just to show you how much you need to actually have a feedback of boundary conditions of the boundary conditions of the macroscopic model onto your lower scale model, and why we need an HMM to actually do proper estimation of macroscopic properties of materials. And yeah, that's pretty much it.